Hi, I'm Ben-Yaakov. This presentation is about current sensing in power electronic systems. I'll cover here sensing current by a resistor, linear current transformer, pulse transformer, and some aspect of the design of a pulse transformer, active current sensing, and finally applying parasitic resistance of the inductor to measure the current. Now, why do we need current sensing in power electronic systems? We need it for control, for feedback. In some systems, you like to have both a voltage and a current feedback, protection to shut off the system when the current goes too high, and information about the power level of the system. The simplest way to measure current is, of course, to use a resistor. We have a resistor, here is the current passing through it, it develops a voltage across it, and you just measure the voltage, you know the current. One thing to watch is the parasitic inductance. There is always a parasitic inductance in any device, and as a result, when the pulse is coming through, and many of the currents we are going to measure are going to have a pulse shape, so as this pulse is coming in, you may get some spikes. So you should look for special resistors for current sensing, which are characterized by very low inductances, and there are some devices like that. Now, there is a problem with measuring the current by a resistor, and one of the problems is the power loss. The power is Ri square RMS, or VRMS times IRMS. In the case of current sensing, you'd like to get a voltage, and this voltage has to have some value so you can use it with a simple amplifier. And if it is a simple circuit, not a special device, the order of magnitude you like to have is about 100 millivolt. So the power that you'll be dissipating in the resistor will be this 0.1 volt times RMS, and if we'll take an example of, say, 10 amps, we're talking about 1 watt. So as the current goes high and high, obviously the power loss will be unacceptable. A way to go around it is to use special devices that are designed for current measurement. These are actually amplifiers. They have, however, three features which are very important in current sensing. The first one is the fact that this common mode voltage could be very high. In this particular case, it's 36 volt. There are some other devices. By the way, this is just an example. There is no endorsement implied here. There are many other vendors who offer similar devices. So one of the features is the fact that this common mode can be very high. This is very important because if you'd like to measure a current which is sort of riding on a high voltage, this would be extremely useful and, of course, very important. Now, the nice thing is that the power supply of this device is rather low. So it's a 3.3 power supply, while you can go up to 36 volts, and some other devices will go to a higher voltage. Another feature which is very important here is the fact that the DC offset voltage of these devices is very low. Now, this is important because if you like the dissipation, the power dissipation of this resistor to be low, you need to have a low voltage across it. So if you have a small value resistor, the voltage will be low, and of course DC offset voltage of the amplifier might cause an error. Now, these amplifiers have low offset voltage. Here's the characteristics of these devices. This is a family of devices depending on the offset voltage. And as you can see, we are talking about in the range, say for the max, in the range of say 30 microvolts. Well, if the DC offset voltage is 30 microvolts, then you can actually measure, say, 1 millivolt fairly accurately. This means that you can have a very small size resistor and the power loss will be very low. These devices, of course, have some input bias current, but this is less important here because the current through the resistor is extremely high as compared to these values. So this is of less importance. This is extremely important, and so this is a high quality device. Let me now turn to other methods of current measurements. One way that one would think is a possibility is to use a transformer. Here we have an inductor, we have the current, here is the transformer, and we'll have the output current here. However, transformer does not transfer DC current. It will only transfer the AC component. That is, the output will look like this. If this is the inductor current, there is no DC transfer through the transformer. Not only that, the DC actually can cause a saturation of the transformer. So this is really not a way to go. However, a similar method for the measuring the current is the pulse current transformer. Here we are using this arrangement for measuring pulses, that is, without a continuous current. We have here a transformer. The primary, this is where we are feeding in the current, has one or more turns, but of course fewer turns than the output. This is the output, and we'll have a large number of turns. And we are feeding this pulse, say this might be the power MOSFET current, feeding it to the primary. This is the primary, and we feed it here. Now during the pulse, we're going to have a current going through here and a current coming out at the ratio of 1 to n. That is n times lower in this case than the input current. This current is now pushed through the diode to the resistor, and here we are going to have a voltage which will look exactly as this current at the primary. So this will be the output voltage across this resistor. This is very nicely duplicating the current of the primary. The output will be the current of the primary times the resistor over n. This is the turns ratio number. Now the question is, what happens next after the pulse is gone? Well, in this case, we have no current at the primary. However, we have a current buildup in the magnetization inductance of the transformer. Here it is, and there is a current here because we had a current coming out. There was a voltage here, and this voltage caused the current to rise actually linearly. And as the primary pulse is off, gone, still we have this current. And this current has to be reduced to zero in order to reset the transformer. Now, usually we'll put a resistor. This will provide a path for this current, and the current will decay. However, the wave shape of this current and the voltage across this resistor many times will have a sinusoidal waveform. The reason is that you have parasitic capacitances at the winding here, and with this inductance, it's actually a resonance circuit which shows up here. Now, for reset, you need this area to be equal to this area. This time is the on time of the pulse, and you do have then to provide sufficient time for this reset, so that if the duty cycle is very high, there might be not sufficient time for the reset, and actually the transformer might go into saturation. So this is something to worry about. So the circuit we have here during the off time is the current going through this parasitic capacitance. There's another diode here. This is the diode being reverse biased. And this actually has a waveform, and the current will have a waveform of sinusoidal wave, and this will be the voltage here. Now the voltage here may be high, and this is something to worry about because this diode is reverse biased, and if this voltage, which is negative, is just getting too high, it might damage the diode. So this is something to worry about. I'll talk about it next. But before that, let me just say that in many applications, you really don't have to put the resistor because the capacitance is so high that it is sufficient. However, you do have to provide sufficient reset time for this process to complete. And again, if the voltage that builds up during the off time, during the reset, is just too high, this diode might be damaged. So in order to protect the diode, you can put a clamp. This is a Zener diode. This is the direction that the Zener operates. So the voltage will be clamped to the Zener voltage. you do have to put another diode, because if not, during the on time, during the pulse time, this current that goes in here will have a short through the zener if there's no diode, because the zener in this direction is like a diode. So in order to avoid that, you do have to put a diode in this direction. So what will happen is that this voltage, this clamp network will clamp the voltage to a certain value, save for the diode here. Again, you have to make sure that the reset time is sufficient. Now there is a question where to put this pulse transformer. There are actually, if we talk about the area around the switcher, around the MOSFET transistor, you can either put it at the drain side or you can put it at the source side. It's not a good idea to put it at the source side. The reason is that there is some inductance here, although it's one turn normally, still this one term has some inductance to it, and this one inductance may affect the rise time and fall time of the transistor current, so that the best or better way would be to put the transformer at the drain side. And there is actually a way to use this idea of a pulse current transformer to measure the full current of the inductor. And the idea is that this inductor current is actually split between two currents. This is current through the diode and current through the MOSFET. And we can see it here. This is the current through the MOSFET, and this is through the diode. Now, on each of these, you can put a pulse transformer to measure it, and then you can combine it. Here it is. Here, we have one pulse transformer that is measuring the current here, pulse transformer measuring the current here, and then you combine these in order to get a full representation of the current in the inductor. So you sort of reconstruct this inductor current. This is a neat way, although you, of course, need two pulse transformer. So let me talk now about some issues with pulse transformers and also go into the question of how to design them. The current that is fed to the primary, as it comes out, the secondary is actually split into two currents. One is the one that goes into the resistor. This is something that we want this resistor actually develop the voltage that we are measuring. However, this part here, which is the part that goes into the magnetization inductance, is actually subtracted from the total current that's coming here. So therefore, we are not measuring here the actual 1/n current of the input, but rather a lower value. So therefore, we would like this current to be much lower than this current. So the impedance of this thing has to be much lower than the impedance of this. Now, one, say, rule of thumb would be to say that the impedance 2 pi, the linear impedance 2 pi fs Lm, this is frequency of switching frequency, Lm is the inductance, should be larger than R. Now, at low frequency, when F switching is low, this might cause a problem. So therefore, in the case of low frequency, you will always have a larger transformer because you need a large Lm. Now the question is, how do you really select the core? How do you select the core? Contrary to intuition, the core size is affected not by the current that we are measuring, but rather by the voltage that is developing here. And this is because the limiting factor here is the B max, that is the magnetic flux density, and the maximum value that you'd allow. This is usually, in this case, will be pretty close to saturation. So the magnetic flux density is a function of the volt second, this is the integral of volt over time, and then divided by the number of turns, and AE, which is the cross-section area of the core. Now, what is this expression here, volt dt? Now, this is the voltage that is on the secondary, and T is the time. The voltage on the secondary is the voltage at the output plus the diode voltage. Now, usually the output voltage here, for reasons that we'll see in a second, will not be very high. Otherwise the core will have to be very large. So therefore the voltage drop on the diode is not really negligible here. You have to take it into account. So the total voltage here is the output voltage plus the diode, here it is, times the on time. So this will be the volt seconds. Now this on time can be expressed as the duty cycle over frequency. So B max will be the average current at the primary. This is the current here. This is not the current, but it's the waveform of the current, and divided by n, because of we have a 1 to n transformer, times R is the voltage that we see here, plus the diode, times D max, and divided by F, and then we have here the cross-section area of the core. So once you know all these, you can select the cross-section area of the core. Now obviously, if you like to have a high voltage at the output, that is a large R times this expression is the output voltage, you need a core with a large cross-section area. So this is the way to choose the core. Another and more sophisticated way to measure the current would be with an active device, like shown here. In this case, we have a transformer. We have the primary winding. This is usually one turn. We have then an element that measures the magnetic field within the core. So what happens is, once you have a current at the primary, there is a magnetic flux building up, and this element is actually measuring the magnetic field in here, and there is a feedback here. It's a negative feedback, so that the voltage measured here, which is in the millivolt ranges, is amplified, and a current is generated to reduce the magnetic flux. So this current times n times at steady state, when the flux is actually reduced to zero, IF times n will be I input times 1. And therefore, this current is a measure of this current. And this current now is flowing through this resistor, and you will sample it here. This output voltage then will be the current times n, because this is the turns ratio, and times RS, this is this resistor. So this device is actually measuring DC current, also AC, and depending on the type of amplifier and feedback, you can measure the current to fairly high frequencies, and you can find devices with a bandwidth of few hundred kilohertz. Finally, I like to show a neat approach, very clever, of measuring the current, say the inductor current in this case, without adding anything, just with an added network here. To explain this, let me just go to this equivalent circuit. This is the current which is passing through the inductor, and I'm sort of bringing it into sinusoidal waveform. This is like Fourier transform, you might say. This is the path of the inductor, and this is the path of this filter. Here it is. This is this filter. Now the impedance of this path is much, much lower than this, so the current actually goes through here. Very little current goes in here. So what will be the output voltage at the of this filter when connected like this? First, we'll calculate the current times this impedance. Here it is, current times the impedance of the inductor. This is the voltage across the assembly here. And then we have sort of a filter or a voltage divider, 1 over j omega c. This is this impedance over the total impedance. And here is the expression, and I'm taking out this RS off the brackets, and I'm getting here IRS times this expression. Now, if this expression is 1, then the output voltage is actually I times RS. That is, what you'll measure here is proportional to this current. Very, very neat. To make this one, you have to have the time constants here equal, that is RC equal to L over RS. So if you choose RC in this way, you'll get an output which is equal to I times RS. Beautiful. Now, this would be the way to actually implement this idea. You have the filter, then you need a differential amplifier because this is a floating voltage. You like normally to get the output referred to ground, so this should be a differential amplifier. And usually you'll have some gain here so that you have a V out I times RS times G. This would be the output voltage proportional to the current flowing through this inductor. It would seem that you can connect this network the other way, but that's not a good idea. That is, to put a capacitor in here, that's not a good idea because this point really has a pulsating type common mode voltage, which would mess up the signal at the output of this differential amplifier. So therefore, we would rather go this way, always connecting the capacitor to a stable voltage, which is, in this case, the output voltage. So this brings me to the end of this presentation. I'd like to thank you for the attention. I hope you found it interesting, and I also hope that this material will be useful to you in the future. Thank you.